Welcome to the mini lecture for Chapter 12 here in Physics 1301. Mechanical waves. So here are the goals for Chapter 12: to describe mechanical waves, superposition, which also includes standing waves, interference, frequency, and Doppler effect, and the beats and how they're related to interference. So let's just run through these pretty quickly here and try to make some sense of them. Mechanical waves in a fluid are the result of some kind of disturbance, mechanical disturbance. Here you can see the water dripping and hitting the water, and that frequency of the water drops hitting the water cause the waves in the whatever that water container is, or lake. At the right, you can see that. So let's look more closely at that. Here in the types of mechanical waves, and there's three in your book. Different books use different terminology. I like this terminology with this text. Transverse wave is a wave in which the energy is perpendicular to the direction. So in that kind of wave, following the cursor, it's going to make like a sine wave or a cosine wave, and the energy is going vertically while the direction of the wave is going forward, and that's that perpendicular propagation. The longitudinal wave is like a sound wave. By the way, transverse wave would be like any of the electromagnetic waves. Longitudinal wave is the disturbance parallel, and so in the case of this, it's like a sound wave where you have the sound, some type of vibration occurs, and so in a longitudinal wave, or some books call it a compressional wave, you'll get a disturbance, a vibration that will literally compress and rarefact or create a vacuum of air molecules that are surrounding it. So I have a tuning fork here, and these tuning forks are used for that purpose. To when they're struck, they will have a natural frequency that always rings at the same frequency. So this one here is 512 hertz, which is the note of C. So when I strike it, that C note is produced because these tongs are vibrating 512 times a second. And your ear then is receiving pressure packets, if you will, every 512 times a second. And your brain then interprets that vibration as being the note of C, or at least that sound. If you have a different tuning fork, so this one, and that's 320 hertz, so it's lower. It's a lower frequency, has less energy. It's vibrating more slowly, and that is an area of high pressure hitting my eardrum, followed by an area of low pressure. So the eardrum goes in on the high pressure, comes out on the low pressure, in on the next high pressure. So the eardrum vibrates at 320 hertz, and that will then correspond your ear, even if it can't tell it's an E. If you don't have perfect pitch and can't hear all these notes, you at least can tell that it's lower perhaps than the other tuning fork, which rang as a C. And that's longitudinal waves. And the third type is a water wave. A water wave is a combination of both of those waves, in that you have, the example of that would be if you dropped a styrofoam cup on out on the lake. If you're out in the boat and you drop it overboard, and the styrofoam cup is both going to move up and down, which is a transverse motion, but it's also going to drift towards the shore or wherever the current takes it, and that's the longitudinal. And so it's a combination of both, and that's how they define a water wave. Here are the parts of a mechanical wave, and this is a transverse wave that we're seeing here. And you have a crest, trough, crest, trough. The amplitude is the height or the depth of the wave, the measurement from the crest to the rest position. And then you also have the so those are the parts of the wave. The wavelength, as I said, was crest to crest or trough to trough, a measure of one full cycle. The formula for wavelength is the velocity of the wave equals the wavelength times the frequency. That would be with the wavelength being measured in meters in the metric system, frequency in cycles per second or hertz, and the velocity of the, the velocity is in meters per second here. The wavelength is in meters. I think I flipped those. Sound and air, sound and water and light all travel at different speeds. Air, we hear sound, but if you're underwater, you hear someone maybe saying something to you underwater or making a noise. It sounds different, and that's due to the fact it's traveling at a different speed. Metal, it travels very quickly in most metals, so make note of that. And temperature and sound and air is usually referred to at 20 degrees Celsius, which is 340 meters per second. And then as temperature goes up, because there's more energy in the air, you get a faster speed for the travel of the sound. So again, here's some longitudinal transverse wave comparisons. Again, the compressional wave or sound wave, you have area of compression followed by an area of rarefaction, which is basically a vacuum, and the wavelength is measured from your same place on the compression to the next compression, and that's how you determine what the wavelength is, and then the speed is going in the direction of the energy as well. That's that longitudinal idea. The transverse, you're seeing the propagation of the wave going in a, as they describe it here, sinusoidal path, and it's perpendicular to the direction of the wave. And so that's the key thing to remember between the two of those. This problem is referenced in your e-text. One of the nice features on the e-text from this this version of the text, is that they do work some of these problems out for you, or one similar to these, and it's a good way to see some of the problems worked out. So I would encourage you to take a look at your e-text and go through a couple of these problems and see their application. So what about when waves reflect? So certain waves have certain properties. Waves have the ability to reflect. They have the ability to refract. They have the ability to diffract. And so when we have a physical wave and it hits a barrier, it's going to return. It's either going to return in a inverted way, so it comes in this way and then returns the opposite, or it's going to hit and reflect and return what's called an erect wave. So you have an inverted wave and an erect wave, depending on the surface that it's striking. And that's a property that waves have. Now, what happens if we put waves on top of each other? And so let's see if we get a good picture of this here. Not the image that I'd like to have, but we'll try to make do with what we have. So here's a case where you have a wave coming through and another wave coming this way. They're both going in each direction. They superimpose on each other, and then they just continue on going. So they just sort of go the other way, and there's no real effect on them. However, if you have one wave coming, and they're exactly out of phase with each other. So a wave is creating some type of frequency, and then you somehow have a wave go at it at the opposite phase or out of phase frequency. So it's the same frequency, however, instead of being in the positive, it's in the negative on the graph. Then the result of that, in terms of sound, in terms of mechanical waves, would be the nullifying of that wave. This is sort of how noise canceling earphones and in cars, automobiles, how they use this to try to improve the sound quality. So the sound, the road noise in a car, the road noise is received by a sensor, and that road noise then is analyzed by the computer, and then an out of phase of that noise is then sent out, and those two, for the most part, nullify each other and gives you a quieter ride. Obviously, it doesn't take out all sound. It's not the cone of silence from Get Smart, but it at least greatly decreases the amount of noise, distracting noise that occurs in a car. Noise canceling headphones work in a very similar way, so it's a very important technology. Here you have what's called a standing wave, and so the wave is being sent and it's reflecting off of the wall or whatever and reflecting back on itself, so it looks like it's just standing there. If we increase the frequency, we get 1.5 waves here, or excuse me, 1 wave here reflecting back on itself. Then we get 1.5 coming back on itself, and then 2 wavelengths here, and all of those are standing waves. These points are called nodes, and the peak and the crest and trough are called the antinodes, and they're the maximum. If you grab this string at the node, it will still continue to propagate. If you try to grab it at the antinode, you'll destroy the wave. This is referring to the resonating mathematical relationships between fundamental frequency, first overtone or second harmonic, first overtone, third harmonic, second overtone, and so forth, in terms of the relationship mathematically between those lengths. Very strong application to those who maybe have taken band or play an instrument and so forth. You maybe have dealt with this in a practical sense.